Hello everyone, welcome to NFX302 session. My colleague Ankur and I are going to talk about media storage at Netflix, its evolution, scale, and our data lifecycle management solution. My name is Isha and I work with content infrastructure and solutions team at Netflix. To give the highlight of agenda we have today, we'll start by setting the context about production lifecycle and Netflix Studio ecosystem. Then we will deep dive into our main topic, which is Content Drive, our studio metadata management platform. It's our motivation to build it, its high-level architecture, design and concepts, followed by stats and numbers. We will also provide a sneak peek into its evolution to support hybrid storage at Netflix in the context of Global Studio. Then I will hand it over to my colleague to talk about data lifecycle management solution in detail, and we will end the show with concluding notes to answer your questions. Let's dive right in. Netflix has pioneered the studio in cloud, giving its artists abilities to work from different corners of the world in creating stories and assets that entertains the world. Right at the point of the ingest, where data is produced out of the camera, it goes through many stages and phases. Some of those are shown here. The media undergoes constant transformations with frequent uploads and downloads happening during all these stages and phases. In order to support these globally distributed processes, we need to provide a highly efficient and performant media cloud infrastructure. Let's start with Netflix Studio ecosystem and how it looks like. At Netflix, we have many applications which work with studio assets and data. Most of these applications run in AWS clouds. When it comes to data, these media assets are what used in post-production to build the final content that you see on Netflix streaming platform. All this data generated during production and post-production is stored in AWS S3 as objects. At Netflix, we store an identity of these objects along with other essential metadata to be addressed by storage infrastructure layers. At the edge, where artists and artist application work with these data, they expect a file folder interface in order to have a seamless access to this data without needing a translating agent in between these objects and their applications. We wanted to make working with studio application a seamless experience for our artists. This is not just restricted to artists. Even studio workflows have this need. A good example is asset transformation that happens during the rendering of a content. So we needed a system that could provide ability to store, manage, and track billions of media files at Netflix while keeping a familiar file folder interface, which lets user upload free-form files without needing a translating agent and provide management capabilities such as create, manage, copy, move, delete, download, share, etc. In addition, we wanted to provide the dynamic access control over these files and folders, which could change per project, per stage, with asset, with workflows, or with applications or users. In addition, there's a need for providing collaboration and sharing features to our different production departments, where they can choose to share any file, folder, or any other asset to any user or application or workflows. In addition, we wanted to always ensure that we support disparate new media enhancement and features and provide them as first-class features in this application. So we came up with the concept of Content Drive, which can be leveraged in multiple scenarios. So what is Content Drive? In simple terms, Content Drive is a metadata abstraction layer on top of Amazon S3. It's a file folder metadata abstraction. Note that. So we create a file folder metadata abstraction on top of the objects that are actually stored in Amazon S3. This gives us huge advantage. For example, this provides us rapid file operation capabilities where we can allow users to create copies of this data or move this data without needing to move or copy underlying bytes. In addition, this content drive can provide dynamic access control where users can control the file folder access or based on their applications or workflows. Content drive also facilitates data transfers where it can help creating data transfer sessions and then provide authorization tokens to do the actual transfers. Content drive additionally provides rich set of file folder notifications which users can leverage in multiple scenarios. For example, Content Drive provides an upload complete notification when a file or folder upload has completed. In addition, we have capability to audit each and every move or change that user is making to their workspace or any application or asset. Let's take a look at high-level architecture. So what are the different components? We have a REST and GraphQL layer, which provides endpoints where users can access these files and folders. They can create, they can manage, they can copy, they can share, they can download, etc. There's a file service layer, which is the main service to perform the actual operations of managing this metadata structure. Access control layer provides features to perform the actual sharing of these files and folders to different users and applications. Data transfer layer is leveraged to generate the authorization tokens for these files and folders and create transfer session track transfers for uploads and downloads of these files and folders. Persistence layer does the actual work of maintaining this metadata structure by performing the actual DB operations to maintain the metadata. We have an event handler that gets the notifications from our object layer and then sends the file folder notifications to the applications for their consumption. A good example of Content Drive backed UI is shown here, where a user accessing their personal workspace in cloud can perform operations similar to those that are performed on local file system. For example, like file folder creation, copy, deletion, listing, sharing, and so on. As I mentioned before, the API layer that C Drive provides are REST and GraphQL endpoint, and it also has a Java SDK for applications to be able to perform these operations on the files and folders. Some of the API examples are shown here. For example, there are lots of batch APIs such as bulk get, bulk fetch whole tree or summary of the whole tree or getting the listing of that directory or folder or size, etc. Now let's dive into some of the core entities to understand the system in detail. In C Drive or Content Drive, we store files and folders in hierarchical tree structures. All these file folders or workspaces or partitions are represented by a node structure in C Drive, which is called a C node. So what are the different C node types? We have the top level C node type, which is a root or a workspace. This is analogous to a disk partition or OS. This is created to have a namespace for the files and folders underneath. Then we have a folder, which is a simple container node. We have a file, which is a leaf node, which has a reference to the actual data location where the object is stored in Amazon S3. We also have a concept of special node, which is a sequence node. Sequence is a special node or container in Content Drive, which can contain millions of files underneath. This is created to represent special media files such as off-camera footage, which has a range of frames that form a small clip. This is a special media feature that we have added in Content Drive to help our consumers understand the media underneath. And then another special container that Content Drive provides is Snapshot. Snapshot is a special container that guarantees the subtree under it is immutable. Typically, applications create the snapshot to lock the files and folders to create the spinal assets. Now let's look into further design concepts. How C drive maintains the parent-child hierarchy. Each C node stores a reference to its parent. That's how C drive maintains the hierarchical tree structures. Type and correctness are very important so that we maintain the consistency and correctness of our data. That's why we maintain a unique file path invariant where each file path will be represented by a unique C node all the time, which means at any point in time, name, parent ID, and partition ID will always be unique in C drive. We have to support distributed transactions so that we can support the complex batch operations or copy, move, or listing. We have normalized the data locations for files, which means we only store one copy of data location where each file C node will have reference to the same copy of data location. We have a strong consistency and complex query support in our persistence layer so that we can provide batch operations and support instant copy and move operation with consistency guarantees. A C node goes through many different states during its life cycle. Let's take a look at those. At the starting, when C node is created, it means that it is just a creation of the metadata instance of that node structure for a file or a folder. Once the upload completes, it moves into an available state, and then internally when the checksums are created, then it moves into checksum verified as the system verifies the checksums for files or folders in that structure. A C node can also get soft deleted based on user-based action, and C node can also be recovered based on user action. So all these are APIs that are provided by Content Drive. Now with the data lifecycle management, we have added additional states such as archive, where a C node, once it's verified and the production has launched, we don't need it in active live system. It is moved to the archive state where the actual data bytes are stored in Amazon Glacier. And a C node can also get restored based on production requirement. If a new season is renewed, it gets temporarily restored, or it can also get purged in case it's not needed any longer. So what are the different metadata types that are stored for each C node? For each C node, these are only limited set of metadata that we have listed here. For example, we definitely have a unique UUID that we generate for each C node, which is a node ID. It has a reference to its parent, so it has a parent ID. It has a reference to the data location in case it's a file node. And we also store the checksums and then checksum status for each of the node. Let's take a look at the workspace types. So in C node, we have 3 different workspace types that we support. We support user and personal workspace types, where it is owned by a user and a user has full access to its data, and user can share, perform any operation on its, it is similar to how they will access their local file system. They can perform any operation in their user or personal workspace. This is where artists store their work in progress files. And this is where the data is mutable. And then there's another type, which is project workspace or application-owned workspace, where the data is owned by the application or the workspace or the project, where it doesn't have, individual users don't have capability to access unless the files and folders are explicitly shared with those users. In this workspace, we store the final assets, so that's why its access control is managed by the application or the team. Next, we have a concept of team workspace, where we want to provide capability of sharing of the workspace with multiple users. Imagine there are 2 workstations used by 2 different users, but they want to access same workspace folder in the cloud. They will be able to see the changes made by each other and access these files and folders as if they are local file system. Authorization. Now let's take a look at how we handle the authorization in Content Drive. Authorization is done based on the workspace type. If it's a user or a personal workspace, then authorization is completely controlled by that user. That user can provide shareable access to other users or other applications. But if it's a application-owned workspace, then Content Drive has a concept of delegated auth, where we delegate the authorization request to the application that owns the workspace. What are the different permissions that we allow? Permissions are read, write, share, or download. All these permissions are stored as access control lists in our authorization service. Now let's take a look at example of a user workflow where asset is ingested and how it flows through the system and how Content Drive is leveraged for that. So what are the different entities that are shown here? We have a data ingestion technician. We have a UI that is there on that workstation that is accessed by the data ingestion technician for ingestion of the asset. We have a UI backend application which talks to Content Drive, and we have Amazon S3 where we store the actual bytes, and we have our asset management platform. So what happens when artist opens his workstation to view his workspace? This results in getting their personal or user workspace based on user credential from Content Drive. When artist drags and drops the files and folders from local workstation into the workspace UI, this results in following steps: creating of the directory structure in Content Drive, then creating of the transfer tracking session in Content Drive. This is followed by getting the transfer auth tokens from Content Drive so that the local workstation can perform the actual transfer. Workspace UI gets these authorization tokens from Content Drive and passes them to local transfer agent, which does the actual transfer of these bytes to Amazon S3. Once the data is transferred successfully, Content Drive handles the event notification from our object access layer that object has materialized or bytes are available now. Once the checksums are available in cloud, Content Drive does the checksum verification for the whole transfer and provides the user notification about upload completion. This is followed by an asset creation, which is done on demand based on the process. Modern Netflix Studio has different workflows that can span Netflix Cloud or vendor or our on-prem infrastructure provided by Netflix to its vendors. We want to make sure that Content Drive can be leveraged even for hybrid storage in the context of Global Studio. Now imagine each file in Content Drive can be located in multiple locations. As shown in this figure, that some of these files, if they are available in local vendor environment or our on-prem infrastructure, you can create a representation of this data in Content Drive to have it tracking and visibility on these files. And then you can have operations available to you, such as uploading or backing up these files into cloud or Amazon S3, or hydrating another location with these files, and so on, and perform checksum verification and many other operations. So Content Drive in future is going to be leveraged for all these operations, where the files could be located anywhere in the global studio in Netflix. Next, I want to share some of the insightful stats and numbers for Content Drive to provide more clarity and business value. So as of October 2024, we have about 14.5 billion Content Drive nodes or C drive nodes, where about 848K of them are workspaces. On average, we create about 50 million new C drive nodes every week. As you can see, most of these are files. We do have concept of file, folder, snapshot, sequence, and workspaces, but most of these are file nodes. This graph shows the daily active visits on C drive backed UI page. Here you can see that on daily basis, about 50 to 60K users access the Content Drive backed UI page to perform their operation, to access their work in progress file to create the final content. UI page visits by various studio production departments further highlights the importance of Content Drive for the business. You can see that various production departments, marketing department, post-production, content acquisition, public relation, dubbing, all these departments and many more access Content Drive on daily basis. This graph provides a summary of metrics for server level request per step and overall P90 latencies for the endpoints taken over a window of 2 hours. You can see that we always maintain the P90 latency below 0.5 seconds. We have a goal of even improving it further with our scale. Before moving on to our next section, I want to share some of the optimizations that we have adopted to improve our system's efficiency with scale. We use distributed caching for persistent objects to avoid querying DB for each and every request. We use follower reads in our read queries wherever the data is not sensitive to the staleness. And in order to make sure that we always get default ID-based sorting in our paginated queries, we use time-based UIDs for our node ID generation. We also provide concurrent batch write support for the application where they need very high throughput for the writes. We use common table expressions wherever we know that DB offloading the transactions to DB will be more useful. And another example of latency improvement is shown in these graphs here, where we have shown that by using unique filters in the query, we improve the performance or P99 latency from 18 seconds to less than 1 second. Now I want to hand it over to my colleague Ankur to talk about data lifecycle management solution in detail.
Thanks, Isha, for that insightful overview of Content Drive and how we use it to store and access content at Netflix. Hey, everyone. Welcome to reInvent. I'm Ankur, and over the next few minutes, we'll explore storage lifecycle offerings in Content Drive, examining the technical challenges and the solutions we employed at each point. At a high level, storage lifecycle management refers to the journey that content takes from the beginning to either eventual deletion or move to a permanent storage tier. It all begins with creation, whether that's a camera shot being uploaded or data generated by one of our systems while processing. This is where we establish our first touch point with content. Once content enters our system, it goes through a critical processing phase. This is where we are tagging content, classifying it, editing and encoding it for different systems down the line, and enriching it with metadata. Think of it as creating the stuff that you watch on Netflix. During the processing phase, the content is in active storage, the most dynamic state. This is where most user interactions happen, where modifications are frequent, and where we need our highest performance storage. This stage typically demands the most resources, but also serves our most critical business needs. As content ages or usage patterns change, we move into the transition phase. Using analytics and policy-based decisions, we automatically migrate content to more cost-effective storage tiers. In archive, we're looking at long-term preservation of data, immutability, and ensuring that we can retrieve content if needed, even years down the line. Finally, when content reaches the end of its life cycle, if it ever does, we need a secure deletion process. This isn't just about pressing delete. It's about ensuring we are deleting as much as possible, but not a byte more. And having worked with data for such a long period of time, I'll happily argue that deletion is the most difficult part of dealing with data. So, why focus on it now? We're seeing a perfect storm of growth factors. Our content volume has doubled year over year, driven by three key elements. First, our geographical expansion has introduced new data streams across multiple regions. Second, we have scaled to thousands and thousands of vendors, each contributing to our data ecosystem. And third, in order to shorten the duration of content production, we are seeing significantly high volumes of data movement, both uploads and downloads. But this explosive growth isn't without its costs. We are experiencing a 50% year-over-year increase in our storage and access costs. But here is where it gets interesting and concerning. With an increase in actively used data, we're also seeing a proportional increase in unused or dark data. This creates a significant efficiency challenge for us. Think of it this way. We are not just paying for the data we use, but we are paying premium rates for an increasingly large volume of data that provides no business value to us. The trends make it clear we need to be smarter about our content lifecycle management. It's not just about storing more, it's about storing the right thing. Let's now take a look at how we can address these challenges by leveraging our access patterns. This graph tells a fascinating story about how content access patterns evolve over time. Notice the initial spike. 53% of all access activity happens before title launch. This is when content is actively being utilized by our apps. This is the processing phase of the life cycle we talked about. But watch what happens after a title launches. We see a dramatic drop-off in access activity. At 1 month post-launch, access rates drop to about 8%. By 3 months, it is down to 5%. 6 months out, we're looking at 3%, and by the 12-month mark, access is just minimal. These patterns are incredibly valuable as they help us make smart decisions about storage tiering. Why keep rarely accessed content on our most expensive, highest performance storage? Think about the implications. If we get this right, we can right-size our storage infrastructure, we can optimize cost, and we can still maintain appropriate performance where it matters most. With context set on the opportunity, let's dive into the critical requirements that shape our lifecycle management system. First and foremost, we need policy-based automation. Manual intervention simply doesn't scale. Security is paramount. Every data movement, every transition must be properly authorized. Real-time insights into storage and usage patterns are essential. We need to understand not just where our data lives, but how it's being used or not used. Our system must support object-level granularity in data tiering. We need the flexibility to transition individual objects based on their unique usage patterns or business value. Archival must maintain data integrity at all costs, and purging must be secure, compliant, and irreversible. Comprehensive auditing capabilities give us the transparency that we need. Easy retrieval is crucial as it helps us cast a wider net with our archival policies. And finally, while automation is key, we need the flexibility for ad hoc bulk movements. This allows us to respond to immediate business needs, unexpected situations, without being constrained by automated policies. Amazon S3 already provides a number of storage tiers for us to leverage: S3 Standard, S3 Glacier Instant Retrieval, S3 Glacier Flexible Retrieval, and S3 Glacier Deep Archive, just to name a few. As a part of our evaluation, we took a deep look at Amazon S3's intelligent tiering, which initially seemed promising. S3 intelligent tiering offers automatic cost optimizations by moving data across tiers based on its usage patterns. It's basically the same thing we're trying to achieve here. However, we identified certain limitations that didn't align with our specific requirements. First, the lack of granular controls. While S3 intelligent tiering automatically moves data across tiers after predefined periods, we need more flexibility over these transition rules as it matters significantly at our scale. Second, we can't skip transition tiers. S3 intelligent tiering moves data through a fixed progression of tiers. In our use case, we often need to move data directly to cold storage, bypassing the intermediate tiers entirely based on our business rules. And finally, obviously, S3 intelligent tiering cannot leverage the rich metrics and context that we have about our data. These limitations led us to develop a hybrid solution that provides granular control while still giving us the cost efficiency. Let me walk you through our solution that leverages S3's core capabilities while addressing our specific needs. We have built custom tagging capabilities at the object level throughout our systems. This means we can now make intelligent decisions about tiering based on not just time-based rules, but also content type, business unit, project phase, and even individual object characteristics. When a project reaches a specific milestone, we can now trigger direct transitions to cold storage, bypassing intermediate tiers entirely. Retrievals are easier since we can leverage business context to proactively restore data and save on wait times. Perhaps, and most importantly, we have designed this framework to be storage agnostic. While we have built it on top of S3, the same principles and processes can also be applied to on-premise solutions at the edge, giving us tremendous flexibility for the future. In practice, this hybrid approach gives us the best of both worlds. S3's robust infrastructure combined with the precise control and visibility that we need in our content lifecycle management. Let us now look into the components that shape our lifecycle management system. An asset is a studio abstraction for a set of files and folders and the metadata around it. Millions of assets are generated as a part of each production. Production assets have nature of their own. Some are ephemeral, some are hotter than the others, and some have different levels of importance with time. A lifecycle policy is a set of rules and procedures that dictate when and where data should be stored or deleted. I know we're moving into this world of AI, but our policies are not alive. At least not yet. Now, let's take a quick look into the storage lifecycle management architecture in Content Drive. At a high level, it consists of 4 key components. First, Policy Manager, which translates business context into actionable lifecycle requests. The storage metadata layer, which is the content drive we talked about, which is the brain of the system. A storage lifecycle manager component, which orchestrates lifecycle operations, and the S3 abstraction layer, which translates these lifecycle operations into requests to S3. Additionally, we have other applications interacting with the system to define policies, track metadata, and manage data movement. Let's briefly discuss the role of the 4 key components. Policy Manager provides the capability to store and manage lifecycle policies for assets. This is the brain for determining the next steps in the lifecycle of an asset. Policy Engine evaluates individual policy definitions to determine which assets are eligible for a specific lifecycle operation. This evaluation is typically done in response to a number of trigger events that may occur during the lifecycle of a production, giving us the capability to process these data transitions at any point. Eventually, it queues tasks for the policy execution workers, which then schedules these lifecycle tasks such as archive, restore, or purge with content drive. Notice that I said it schedules lifecycle tasks, as one of our requirements is to be transparent to our users about these transitions. This, however, creates a tangential problem of scheduling these lifecycle events, sometimes days or even months into the future. We've already discussed Content Drive's crucial role as the cloud storage layer at Netflix. But let me walk you through one of the core architectural features of Content Drive that enables efficient lifecycle management. Content Drive fronts lifecycle execution of an asset, receiving archive, restore, or purge events from Policy Manager. It serves a critical function by maintaining a clear separation between the metadata and the data that we store in S3. This separation is fundamental to our architecture and is provided via a reference counting system. Every time an asset is created or modified, Content Drive tracks the relationship between the assets and the underlying S3 objects. This reference count, effectively providing us asset-level deduplication, is critical when determining the scope of these lifecycle operations. When we need to perform a lifecycle operation, Content Drive determines whether we should only modify the metadata, leaving the underlying S3 objects untouched, or also include operations on these underlying S3 objects based on the reference count. Once Content Drive has determined the S3 objects impacted by a lifecycle operation, it hands off this intelligence to the muscle of the lifecycle management system. Storage Lifecycle Manager is the orchestration engine behind all our lifecycle operations. At its heart, it is responsible for managing lifecycle operations that interact with S3 objects. The system is built using a fully asynchronous architecture. When a request comes in, rather than processing it immediately, we first persist it to ensure durability. To achieve high throughput, we have implemented a distributed processing model where operations for different assets are spread across all the nodes in the cluster. And while multiple nodes may be available for processing, any specific asset is owned by exactly one node at a time. This critical affinity is built using Kafka's built-in partition assignment. This sharding approach solves two critical problems for us. First, it increases cacheability and eliminates conflicts that occur when multiple nodes are trying to process the same asset. Second, it ensures uniform workload distribution across our infrastructure. Eventually, the Storage Lifecycle Manager talks to the S3 abstraction layer to tag S3 objects based on lifecycle configurations defined in S3 for the appropriate transitions. Let me walk you through the cost impact of our lifecycle initiatives. The red line represents the initial trajectory. Without intervention, our storage costs would continue to grow linearly. This is primarily driven by data growth and retention of unused assets. However, we identified two key interventions. First, in the short term, we implemented an asset migration strategy to Amazon S3 Glacier Instant Retrieval using built-in S3 lifecycle configurations while we developed our lifecycle management system. This migration alone reduced our costs by 20 to 30% compared to our initial spend. Since we already know that the access patterns for the access activity for older content is really low, this was a low-risk migration strategy for us. Even more significantly, with policy-based storage lifecycle management, we are projecting about 70% cost savings by automatically identifying unused assets, implementing those intelligent retention rules we talked about, and moving cold data to more cost-effective storage tiers. Notice how dramatically these interventions alter our cost trajectory and put us on a path towards stabilization of costs. Let me share some compelling numbers that demonstrate the impact of our lifecycle management system and then outline where we are headed next. We have successfully archived about 77 petabytes of data. Since we are aggressive in our archival strategy, we have had about 200 terabytes of temporary restores over the last year. Perhaps, and most impressively, we have successfully purged about 33 petabytes of content, with lots more to come. And as it is with any storage system, we still have tons of petabytes waiting for policies to be built around. I joked about deletion being the most difficult part of dealing with data, and all of these petabytes are my Exhibit A. Looking ahead, we have three key initiatives that will further transform our lifecycle management capabilities. First, we are expanding lifecycle management to hybrid storage environments. This means seamless management across on-premise and cloud storage, giving us tremendous flexibility in data placement as well as cost optimization. Second, we are implementing an intelligent tagging system. This is tagging content during the production itself, leaving breadcrumbs for the storage lifecycle management systems down the line. And finally, we are exploring metadata tiering. At our scale, it's not just the data, but metadata costs are also significant. Thinking about how we store and manage metadata through a studio production lifecycle guides the next big chunk of cost savings. To summarize, Content Drive is a cloud-native solution for media asset management at Netflix. It empowers Netflix studios to ingest media content, manage its metadata, apply lifecycle policies, and provide access control for content sharing. Content Drive achieves cost optimizations via intelligent utilization of S3 storage tiers backed by our fine-grained pattern analysis. You can find more details about Content Drive and its lifecycle management capabilities in our blog posts at Netflix Tech Blog. Thank you for listening to our talk.